The last type of surface integral we're going to learn are flux-type integrals. And flux-type integrals look like the integral over s of f dotted with ds, where f is a vector field, and I'm going to have to explain what big vector ds is as we go along. So first of all, let me tell you why I'm calling these flux-type integrals. In physics, sometimes you have a surface in space and a vector field, which is defined in a region around that surface. And perhaps this vector field represents the flow of water or something. Then the flux-type integrals are going to calculate the flux of the vector field through the surface. In other words, they measure how much of the vector field is flowing through that surface. So these are often used not just with water flow, but for electricity or magnetism. You'd like to know how much of a vector field is flowing through a certain surface. So one thing that we have to worry about that we've not had to deal with before is that these flux-type integrals are only defined on what are called orientable surfaces. So the surface S must be what's called orientable. So what that means is that you need to be able to make a consistent, continuous choice of normal vector field everywhere on the surface. So you have to be able to define a unit vector field which is normal to the surface at every point. Now, a famous example of a non-orientable surface is the Mobius strip. Wow, I used to be able to draw a Mobius strip. This one's not coming out that well at all. What I recommend, normally I'll tell you that when I teach this class in person, we end up actually making Mobius strips in class and playing with them to verify that they're not orientable. In fact, a Mobius strip has exactly one side. So here's something that you can do. If you've got paper, scissors, and tape available at home, I'd recommend that you take a strip of paper, make it a little bit longer than this, curl it around into a circle, like this, and then these front edges, instead of taping them together just like this so that you get a cylinder, I want you to take one side, turn it upside down, and then tape them this way. So instead of going like this, you're going to flip one side and tape it like this. And then let's imagine that you're going to put a normal vector field on it. That's equivalent to basically painting one side a different color. So you start going along and you paint this side. This continues around the back. You come around here, but because of the flip, because this side is flipped before you reattach, now you're painting the back of it, coming around, and then because of the flip, you end up on this side again. So it turns out that a Mobius strip only has one side, which makes it a non-orientable surface. So these flux-type integrals are not defined on non-orientable surfaces. They have to be surfaces which are orientable, which is equivalent to there being one-sided. It's possible to paint one side red and the other side yellow, for example. So now with that technical condition aside, let me tell you a little bit more about what this ds is. The definition of big vector ds is it's equal to that unit normal vector times big scalar ds, the area element. So you're able to define a unit normal everywhere on the surface. Big ds is that unit normal multiplied by ds. Now, if a surface is orientable, there are two possible orientations. And in each problem, the orientation has to be specified. So let's see how we would calculate that. If we parameterize, remember that d phi du crossed with d phi dv is a normal vector to the surface. Now, it might not be a unit normal, but it is going to be a normal. Since d phi du and d phi dv are tangent vectors, their cross product is going to be a normal vector. I can make this into a normal vector, though, if I divide it by its length. So d phi du crossed with d phi dv over its length is equal to a normal vector. Now, a normal vector field has been specified on this in the problem. So this guy is either equal to that normal or it's equal to its exact opposite. So the vector field n is either plus or minus d phi du crossed with d phi dv over the length of that cross product. Now we also have a formula for ds. ds, we know, is equal to the magnitude of the same cross product times du dv. Well, that's nice. Notice that these magnitudes cross out, and we get the formula for big vector ds, which is plus or minus d phi du crossed with d phi dv times du dv. I'm actually going to erase these parentheses because I don't want you to think about them as being absolute values. And in this, in any particular problem, you have to choose the plus or minus so that this vector points in the direction of the given orientation of the surface. Trying to think if there's anything else I want to say before I move to a new video. The answer is no.